we have a loaded penguin, right? So it weighs 80 newtons at rest on an incline. That's at 20 degrees to the horizontal. Between the sled and the plane, you could see here that we have a coefficient of static friction of 0.25. Warning. They're saying this guy is equal to what? 0.25. 99% of the time, what we assume here is that they mean that that is maximum static friction. Even though they don't say it, the idea here is to assume. Now, by the way, it could be a wrong assumption. We have to do a calculation to see whether this is a wrong assumption or not. And mu of k, that's always a constant, so it's 0.15. So now we can treat static friction not as a variable, but as a constant force. Okay, then it says, what is the minimum magnitude of the force parallel to the plane that will prevent the sled from slipping down the incline? Okay, that's what A is. And then they want to know what's the minimum force F that will start the sled moving up the plane. Okay, so let's go look at those A. So A. Okay, we want to know the minimum force required to stop the sled from sliding down. Question. What is the tendency of the sled? How do I say this? What is the direction that the sled wants to move? And that becomes really important. So is the sled trying to move down, or is it trying to move up? And it's in the phrasing here. The phrasing here, we want to prevent the sled from slipping down. And so what this does here is it answers this question. So what we say here is this: the tendency is to do what? Is to slide upwards. So that friction is up the incline. So let's go draw a free body diagram. So here we go. So what I'm going to do here is that I'm going to imagine that I have my incline. And now I'm going to replace the sled and the penguin as a point. There's my point. So I know I have the force of gravity. I know that I have a normal force. So in this case here, I'm going to call this normal force NA. And what I know here is that the box is trying to slide down. So I know that the motion, now look, let me be very careful here. There's no motion in the box. The box is not moving. But look what I write. V equals to 0 is down. Even though it's not moving, the tendency is to slide down. So when I look at this thing here, then that means that the frictional force has to be in which direction? Has to be in that direction right there. So what we assume here is that because of this, the motion of this guy, we're going to see here is that the force of gravity is going to be great enough to make this thing want to slide down. And so I could come in here and I can write my components for y. So I have to apply a force in this direction, which I'm going to call FA. So look how I got the tendency going down. So here I go. This is 20 degrees. This is 90. That tells me that that is 70 degrees right there. Okay. So when I look at this thing, I could now write down my N2L equations here. I know that this is in static equilibrium. So that means I have to have a balance of forces here. So here I go. So what am I going to do? I'm going to apply N2L. So when I look at this thing here, that means I'm calling that positive, positive, negative. Now note, it depends on how you view the world. You may choose to use the angle 20 degrees, but I'm going to use the angle 70 degrees. Why? More people, from my experience, prefer to measure the angle off the x-axis. So that's what I'm going to do. So here I go. I have the forces in the x. I have the forces in the y. So when I look at this thing, what do I see? Look at mgx. I'm going to get mgx in the positive direction. And then I see that I'm going to write friction in the negative direction. And I'm going to write the force of A in the negative direction. And of course, this has to be 0. When I look at this other situation, I see that the normal A is in the positive direction, and then I'm going to get minus mgy, and of course, this has to be 0. So now, what I'm going to do here is that I'm going to break it into the components now. So the very first thing that I almost always do here is I always write my frictional force in terms of the normal. So here I go. So what do my equations look like? Well, my equations now look like this. I have mgx, so I'm going to write mgx cosine of 70 minus mu of s times the normal of A minus FA equals to 0. And then I look at this guy, this is going to be the normal of A minus mg sine of 70 degrees, and that's equal to 0. So what I'm seeing here is that I now have my N2L equations right here. So this is equation 1, this is equation 2. So what I'm seeing here is that I'm seeing what? Okay. I got the question, what does the force F of A represent? Well, the question that we're asking is this here. What is the minimum magnitude of the force that you have to apply to stop the box from sliding down? Okay, that's what that force F of A is. And I called it A because we're in part A. because in part B, you're going to see that there's a different force, which I will call B, F of B. So here we go. I have two equations, two unknowns. What are my two unknowns? My two unknowns, well, I need the force. So check this out. So what force do I have? That's an unknown. What's the other thing that I don't know? I don't know the normal. And I need the normal to solve for the force. So therefore, in this case, I have an A, FA. So those are what my equations are. So now I got to go solve for the force. So what I'm going to do here is that I need to solve. So we need to determine F of A. So the way I'm going to do that here, what they tell us here is that mg is 80 newtons, and we know the two coefficients. Well, we only need one because it's in static here. So here I go. So what I'm going to do here is that I'm going to solve equation 2 to get an A. So here I go. So from equation 2, we can see here is that all I got to do is I got to take the mg term to the other side. So then I get NA is then going to be mg sine of 70. Now what I'm going to do here is that I'm going to sub 2 into equation 1 to get F of A. So let's go do that. So what you're seeing in 1 here, I got to isolate F of A. So I'm going to take F of A to the other side. So I'm going to get, let me write it over here. I'm going to get, so from equation 1, you could see I have F of A is then going to be the sum of these. So it's got to be mg cosine 70 minus mu of s times the normal. But the normal we see is what? Is this mg term. So I'm going to get mg sine of 70 degrees. So now that I have that, I could then go in and I could then isolate that. So the first thing I'm going to do here is I'm going to pull out mg. So if I pull out mg, then I have the term cosine of 70 minus mu of s sine of 70. And here's what we'll do here. So if I plug in mg equal to 80 newtons, and I plug in mu of s equals to 0.25, the number that you'll get here is 8.6 newtons for the force Fa. So this is what? This is the minimum force to stop the sled from sliding down. So here we go. So this is what it is right here. But now we want to change this here. So what we want to do here is that we now want to do the next piece. And the next piece talks about what? What is the minimum magnitude that will start the sled moving upwards? Okay, so this is B now. So if I look at B, we want to know that now we're going to move the sled upwards. So when trying to move the sled up the incline, friction changes direction now. It's now going to be opposing you, right? Even though the sled hasn't started moving, friction changed directions. And the reason why that becomes important here is that think about it this way here. So if I look at my scenario here, what's happening here is that there is a brief. So now what's happening is that the tendency is the motion. Actually, I'm going to move this over here just to keep it in line with this. What you're seeing here is that now as I'm going up the incline here, those little peaks, the little red peaks, are interacting with the blue peaks, and it's pushing it in the opposite direction now. So when I go and I look at my incline, I have the same situation as before. So now I have 20 degrees, and here I go. I'm going to replace my blocks. So this time, my normal is going to be different here, because I'm calling this part B. So I'm going to say, oops. So I have a normal NB. Again, I have my mg, which means I have my component mgy. I have my x component mgx. But now that my motion is to go in this direction, right? That's the tendency of the block to move this way. Friction has now moved in the opposite direction as I start to push up the incline with a force of FB. So in this case, because the tendency is to be up, I'll put my plus and minus signs like this here for my coordinate system. And then I'll start writing out N2L here. So I'm going to apply N2L, and here I go. So I have my sum of the forces in the x direction, my sum of the forces in the y direction. And what do they read here? Look at my red. It's in what? The positive direction. Look at my other two forces. Friction, in this case, look what I'm writing. Mu of S and B. I don't even like to write friction without writing it as the coefficient of friction times the normal. And then I have mgx. But mgx, we already said, this was cosine of 70 degrees. Again, this thing is in static equilibrium. And if I do the same thing for as before, this normal and B is then being counteracted by mgy, which is mg sine of 70 degrees. And of course, this is equal to 0. So what you're seeing here is that I now have my N2L equations. So I'm going to equation 3 and that equation 4. So I need to do the exact same thing that I did before here, right? I have to do the exact same thing as I did before. So what you're seeing here is that note that the normal is the same as before. So we use equation 2 to get NB. And we already saw that the normal was the y component, so it's going to be mg sine of 70, just as what we saw before here. The question was, in choosing which x-axis is positive or negative, do we always choose the direction of friction to be going in the negative half of the axis? That's what I do. And the reason why I choose that direction here is because I always choose the velocity, the direction of motion, to be positive. That's why you'll always see my friction in the negative direction. It doesn't have to be that way. And so here we go. So now what I'm going to do here is that I'm going to sub NB into equation 1 to solve for FB. So if I do that, you could see here is that if I look at equation, oops, I'm saying 2 and 1. I'm sorry. I should have been saying 3 and 4. So when I look at this thing, here I go. So if I look at equation 4, as before, I now solve this thing. But look at the difference now. Instead of subtraction, they're adding. So now if I put this all together, I'm going to get mg cosine of 70 plus mu of s sine of 70. Okay, so if I look at the numbers again, remember, mg is still 80 newtons, mu of s is still 0.25. And so when I get this number here, I'm finding that this is now 46 newtons. And this is the force of B, and this is the minimum required to start moving. So I now have those two forces here. And what you're seeing in this scenario here is that, look at the two numbers here. We want to compare that F of A versus that F of B. And you could see that there's a fairly dramatic difference between the two. So what is the difference between F of A versus F of B? So the first thing here, we had F of A was 8.6 newtons. And in this scenario here, what we're finding here is that what happened here? Friction was helping to stop the downsliding. On the other hand, when we looked at F of B, which is 46 newtons, what we're seeing in this scenario here is that friction was opposing the upward motion. So instead of helping to keep it up, it's actually working against to stop it from moving. And we have that one term, and that becomes an important term to actually look at this thing here. So one last piece to this problem. Here, I gotta go.
Wait, so you said that friction FB is opposing the upward direction, but our FB is pointing upwards.
No, the friction was opposing the upward motion.
Oh, got it. Yes, of course.
Okay, for some damn reason, I'm having issues of freaking doing this. So now look what's happening now. What value of F is required to move this thing at constant velocity? And so in this scenario here, what we have here is that the block is now moving at constant velocity. So immediately that tells us that it's sliding at constant velocity. So now we have kinetic friction. And so what this really tells us here is that if we're moving upwards, then N2L equations from part B are identical, except we trade out f of s with f of k. So if we just do that, right, it's exactly these equations up here. There's no difference because the tendency was to move upwards. These equations are identical. We just change out that mu s to mu k. So when I look at this thing here, then I'm saying that I have the forces in the x, the forces in the y, and so then I'm going to rewrite those identical equations. So now this is the force F of c, and here's my change. And then I get the exact same normal as before. So these are my equations right here. So since the solving of this problem is identical, then what I'm going to say here is that I'm just going to solve for f of c. And when you do that, this is what you get. It's the exact same equation, but look at the 39. So I now have a force F, C, that's 39 newtons. So if we're going up the incline, so in summary, for going up the incline, what you're seeing here is this, is that F of B is 46 newtons, and this is what was needed to accelerate, needed to start acceleration. Whereas F of C, which is equal to 39 newtons, this was needed to what? To just keep it moving. And you can see that the one for static friction to start the acceleration is bigger. And the question is, why is F of B greater than F of C? Because this involved static friction, which is always larger, whereas this guy involves kinetic friction, which is always smaller. And that's what we are seeing right there.